the first major theme in this chapter, that is the introduction of the capacitor. So, or specifically how to calculate capacitance, and then before we conclude, also just in general from a circuit theory standpoint, know what happens to the effective overall capacitance if they're connected in series versus in parallel. But let's just start out by looking at the parallel plate capacitor, or probably the most basic geometry for us to build some intuition. We have two plates over here, and then we apply a potential difference between them. Let's say that we connect this one side to a potential of V, and the other side we connect to ground. And what ends up happening is that on top you're going to accumulate positive charges on one plate, and you're going to accumulate negative charges on the other. And with charge density of, let's say, rho s and minus rho s. And remember, charges are in the form of electric fields. Charges are effectively arrow generators, right? And these negative charges are arrow sinks. So you can visualize that the electric field will probably flow from the positive plate to the negative plate. Now, usually in between, you have one positive plate and one negative plate. These will just be considered as very thin conductors. If you have it thicker than a plate, remember the charge just accumulates at the surface, right? So for all intents and purposes, we'll consider this as a surface charge sheet. And in between, you're given a dielectric. And the dielectric has some kind of material epsilon. Now let's recall what a dielectric does. A dielectric means that, unlike a conductor where you can just churn out as many charges necessary to cancel this out, the dielectric just creates dipoles that respond to the field. Right? So all of the little atoms in here form little dipoles that try their best to cancel out the field. So they will kind of stretch out like this, where you have a slightly negative side and a slightly positive side. And what that does is it ends up countering the electric field. Therefore, I think the first main concept that I want to get across is that if you have a dielectric, I mean, what's in between is a dielectric, but the dielectric permittivity, the material that you have here, if epsilon increases, then that means that you need more field to generate the same amount of potential, right? Because you have these dielectric dipoles. The increased epsilon means that you create more strength in these dipoles that counter the electric field, which means that you will need more charge to create the same potential, assuming that in all the dielectrics you're able to create a potential of V. It means that you will need more charge in order to create the same level of potential of V volts between this plate and this plate. Now let's start to define capacitance. So capacitance is defined as the total amount of charge stored divided by the amount of potential that was applied to reach that level of charge. And so you can see that if you increase the epsilon, if you increase the permittivity, then that means that you need more charge to create the potential V that you're given. And so greater epsilon will end up increasing the capacitance. And in many cases, when you're given a geometry and a potential, we want to be able to calculate the capacitance, right? So let's start by looking at V. V in most cases is given in many of these situations. So you're often told that you apply some kind of potential along here, and so the remaining thing is to find out what Q is. And in this case, Q would be equal to the total amount of charge across this plate. So given this rho s, you have all the information you need to be able to find Q. Right? And so Q is going to be equal to the surface integral of rho s ds, where ds is the unit surface of this plate, right? And recall that if it was as drawn here, ds would be in this direction. Let's look at this parallel plate capacitor in a different way. So let's use a different graphical interpretation just to build a little bit more intuition. Let's say we have two parallel plate capacitors that we'll consider at the same time, both held to a potential of V. I'll ground one plate and hold the other plate at potential V. And in this case, in both cases, you'll have positive rho s, negative rho s, just like we had described in that prior example. And now let's look at what happens for, let's say V equals 6 volts, as in the lecture notes. Now when we basically define that this is sea level and this is an elevation of, let's say, 6,000 meters. And if this is a uniform dielectric inside, then we know that the elevation is just going to change it's just going to change evenly. So we can draw these equipotential lines. Everywhere along this line will be equal to 4 volts. So this is 6 volts, this would be 4 volts, this would be 2 volts, and this would be 0 volts, right? 4 volts, 2 volts, 0 volts. And so if you think of it from an altitude perspective, I fix this at sea level, I fix this at 6 volts, and I don't really give you any reason to think that there's anything that's non-uniform, then what you would have from a 3D topographical map shape would just be a straight, evenly sloped line downwards, where 1/3 of the way through you're down to 4 volts, 2/3 of the way through you're down to 2 volts, and then you're down to 0. Now let's say this material has a small epsilon. So if this is a small epsilon and this is a large epsilon material, if you want to draw, let's take a look at, if you want to draw the electric flux density. Remember, the electric flux density D is just simply defined as the density of the field lines. Let's say that in order to, for 6 volts with this small epsilon, you need a certain amount of charge that is equivalent to 4 field lines for this region of interest in order to create this amount of slope, this 6 volt slope that you see here. Now remember that if you increase epsilon, now you have this extra electric field that's fighting what you would have applied, right? Therefore, remember D is equal to epsilon E. If epsilon is bigger, that means that to achieve the same electric field, remember the electric field is a slope here, right? So you have the same electric field in either case, but to achieve that same electric field, you need a greater amount of charge, and as a result, epsilon goes up, the electric flux density goes up. In either case, you're going to need a greater density of arrows in order to achieve that same electric field. So in this case, there would be 6 horizontal lines for the same width of area that we're interested in. So 2 ways to look at this. One is you have a bigger amount of rho s. If you already know that this is going to be 6 volts, you need a greater amount of rho s in order to achieve that 6 volts, because you have larger dipoles in the dielectric kind of fighting you and countering you. So the other way to look at it is just mathematically, since D, the electric flux density or the arrow density, is equal to epsilon E. If epsilon increases for the same amount of E field, to achieve the same slope, you will also need a greater amount of arrow density in order to achieve that same E that you need. And so 2 ways of looking at it. But either way, what I wanted to show is that when you go through this little thought exercise, a small epsilon gives you a certain density. If you increase the density, you need to have a greater increased density in the field lines. So the one graphical way to look at this is you can also say that capacitance is the ratio of the vertical lines. So the number of vertical lines for a given region of interest to the number of horizontal lines. So you can kind of use this analogy to develop a little bit of intuition as to what the capacitance means. But in either case, whichever interpretation works best for you is what you should go with. But the general idea is you have two conductors separated by a dielectric. When you apply a potential, charges build up on these surfaces. You get a surface charge density on these conductors. And the amount of surface charge density that you need to create this potential V that you've applied depends on the epsilon of the dielectric inside, because that dictates how much dipoles are popping up to counter your electric field, right? So if you were able to achieve this potential, you were able to apply that electric field. So the question is, what's the amount of surface charge density needed to achieve that? The greater the epsilon, the greater the surface charge density needed, which in turns mean that a greater amount of charge is stored. Or, as we'll talk about later on, the more energy is stored in the capacitor. To start out, I mostly just want to introduce this, give you a few different intuitive ways to talk about capacitance, introduce the basic equation, and just to give a preview, remember that we have the tools to find the total amount of charge just by finding the surface charge density, which, remember, is related to n dot, the electric flux density. And then also get the intuition that the greater the epsilon, the greater the amount of capacitance you have. I'd like to wrap up this segment by just pointing out mathematically what happens when you have capacitors connected in series or in parallel. The reason I want to introduce this is that if you were able to solve for two different if you had a capacitor geometry that can be broken down into multiple capacitors that are either in series or in parallel, you can then use the fundamental equations to solve for these individual capacitors, but then you have to combine them somehow. And the way that's easiest to remember is that it's kind of the opposite land of what we have with resistors. In the case of being in series, you have something that's like the in parallel formula, where the 1 over the equivalent capacitance is the inverse of C1 plus the inverse of C2, or in other words, C equivalent is going to be 1 over C1 plus 1 over C2. Hopefully most of you are familiar with how to navigate this. Just remember that this is in series, not in parallel, but otherwise it's very similar to resistors. And then continuing the spirit of it being opposite to resistors, if it's in parallel, then the equivalent capacitance would just be the sum of the two. So to review, basically gave a basic intuitive explanation for what a capacitor is. Again, two conductors with a dielectric in between. You apply a potential, and the capacitance is the amount of charge that you needed to have that potential occur between these two. And one of the key factors that we described is the material property of the dielectric in between, this epsilon term, where the greater the epsilon, that means that the greater the dipoles that you have within the material that will counter this hard-earned electric field that you're trying to produce. And so the harder you have to work to achieve that potential V. But then that also means that once you achieve it, it took you more charges to get to, so you have more charges stored in there that you can then use to do other things. So in that sense, you have more energy stored. And we'll continue that discussion when we talk about the different capacitor geometries.